Okay, good afternoon, um, ladies and gentlemen. Welcome to our second online lesson, and I hope that the sound is well. I tried, I think last lesson there was a few complications and it wasn't clear, but I hope the sound is well. But before we start, I did get a question from yesterday's lesson, and that question was from Shahid, and that question said, that is here, and that question read, can we use the number of moles equals to mass over molar mass equation at standard temperature and pressure? It's yes, we can. The only two formulae that we can use all three formulae at standard temperature and pressure, but if it's not standard temperature and pressure, then we cannot use the number of moles equals to mass over molar mass and number of moles equals to number of particles over Avogadro's number. So I hope that's clear for everyone, and let's begin today's lesson. So today's lesson is mass percentage, empirical formula, and percentage yield. Now these three concepts are used in a lot in university and in industry. Mass percentage is calculating how much of or how much an element weighs in a compound, and we'll go through that. Empirical formula is finding the formula of a compound, and and percentage yield is determining how much of a product you produced at the end of a reaction, which is very important to know. So let's get into it. We're going to start off with mass percentage. And mass percentage is a method of calculating how much mass of an element is present in a compound. So we have oxygen, we have the compound H2SO4, which many of you know is sulfuric acid, and we want to know how much of oxygen is present in the compound, because you see we have three different elements making up that compound, and we have of we have four hydrogens present in that compound. So we want to know how much of oxygen makes up that entire compound. Okay, so the answer is 65%, and we'll get to the calculation just now. Excuse me. One thing we need to know about mass percentage is that it uses the mass to calculate a percentage, right? And this mass can either be in grams or it can be in grams per mole. Now we use the grams per mole, which is the molar mass, because it gives us a more accurate representation of the percentage of the element. So basically it accurately tells us how much of each element is present in the compound. So that's why we use the molar mass method. Okay, so let's look at some examples. We'll do two examples, and the first example is calculate the mass percentage of the elements in phosphoric acid. So the first thing that we need to know is what is the chemical formula for phosphoric acid. We know that it is made up of hydrogens, it'll have a phosphorus, and it has oxygen. So we need to write down the step one is to write down the chemical formulae of phosphoric acid, which is H3PO4. Okay, so now we see that phosphoric acid has 3 hydrogens, 1 phosphorus, and 4 oxygens. Now we need to look at the periodic table for step 2, so I hope you have your periodic table out. Okay, so notice that step 2 says find the molar mass of the compound not, and we do this find by adding up the individual molar masses of each element. Now we have 3 hydrogens present in phosphoric acid, so we're going to multiply the molar mass of hydrogen by 3. We have one single phosphorus element or atom, and we have 4 oxygen atoms present. So that's 3 times 1 plus 31 plus 4 times 16. The 1 comes from hydrogen and the 16 comes from oxygen. Okay, and that would give us 98 grams per mole. Please don't forget to put in your unit. You don't get a mark if you don't have your units. Okay, now step 3 is divide the individual molar mass by the total molar mass or the molar mass of the compound. So this is how we do it. We write percentage hydrogen equals to 3 because there are 3 atoms of hydrogen divided by 98, which is the total molar mass, times 100 because we need a percentage, which is 3.1%. So what this tells us is that 3.1% of phosphoric acid is hydrogen. Okay, now percentage phosphorus equals to 31 divided by 98 times 100, which equals to 31.6%, and that means that 31.6% of phosphoric acid is phosphorus. Sorry, and percentage oxygen equals to 64 over 98 times 100, which equals to 65.3%, which means majority or most of phosphoric acid is composed of oxygen. Now, if you quickly do a little addition or a quick addition there, you will see that the percentages have to equal 100. If it's below 100, it's okay. It's probably because of your rounding off. But if it's 100, 100.1, that's fine. But you have to get around 100 because percentages are totaled at 100. Okay, so that's your notice to take. When you add the mass percentage, you should get 100%. And we do get 100%. Yeah, we do get 100% for that compound. Okay, we're going to do one more example for mass percentage, and this one says determine the individual mass percentage in the compound C6H12O6. Now, for most of you doing life sciences, you'd know that this compound is glucose. Excuse me. And if glucose is the sugar that we need for respiration, and it gives us our energy. Okay, so let's look at the mass percentages now. They've given us the compound, the chemical formulae, so we don't have to worry about that. Step 2, we have to calculate the molar mass of the compound. So have your periodic tables ready, and you see we have 6 hydrogens, 6 carbons, 12 hydrogens, and 6 oxygens. Okay, so that will be 6 times 12 plus 12, and the 12 is 12 times 1 because the molar mass of hydrogen is 1. and that's 6 times 16 from oxygen. Okay, and that gives us a total of 180 grams per mole. And don't forget your unit, please. And now we calculate our percentages. Now we see that if we take the 72, which is 6 times 12 from carbon, we get 72, and the percentage of carbon is 72 over 180 times 100, which gives us 40%. Now 40% of the glucose compound is carbon. Now we go to hydrogen, and that's 12 over 180 times 100, and that's 6.7%. And we get oxygen, which is 96 over 180 times 100, which equals to 53.3%. Now again, if you add that up, you'd get 100%. Now you'd notice that the more heavier the molar mass of the compound, the more percent it contributes from its mass to the compound. Okay, so what I mean by that is oxygen is heavier than carbon and hydrogen, so therefore it would contribute more to the mass of glucose than carbon and hydrogen. Okay, now if you guys have any questions, please again drop that email and I will respond to you in the next lesson. Okay, or I will respond to you as quick as I can. So we're looking at empirical formula now. An empirical formula is a process of determining the chemical formula from mass percentages. So basically what we're doing is we're doing mass percentages but working backwards to get our empirical formula. So if you notice here, we went from the empirical formula to a mass percentage. Now in empirical formula, we're going to go from mass percentage to the formula. So we're basically working backwards, okay? And it provides us a ratio of elements in the compound. So C6H12O6 is a ratio. It's not the simplest of ratios, but if you do get a simplest ratio, it's 1 is to 2 is to 1. So that's 1 carbon to 2 hydrogens to 1 oxygen. Okay, and empirical formula will help us get this simple ratio. As I said, the process for calculating the empirical formula is the opposite of mass percentage, which means we're working backwards from mass percentage. Okay, so let's look at examples. Now the question says determine the empirical formula for a compound containing 52.14% carbon, 34.73% oxygen, and 13.13% hydrogen, right? So what is our first step? The first step is we're going to assume that there is 100 grams of the sample that we've been given. Now what this is if we add our percentages up, we should get 100%. Now what we're saying is that we take that 100% and we assume that it's 100 grams. Okay, so that we are able to get a mass in grams. Okay, so the mass in grams for carbon would be 52.12 grams. The mass of hydrogen would be 13 grams, and the mass of oxygen would be 34.75 grams. Right, that was step 1. Step 2 is divide each mass by the element's molar mass. So you're going to have your periodic table out again, and Basically, we're calculating the number of moles here. As you can see, we have mass over molar mass. Okay, yes. So for carbon, we have 52.12 grams, and its molar mass is 12 grams per mole, and that equals to 4.34, which we will take as 4 atoms of carbon. Okay, so we're assuming now in for empirical formula only that the number of moles we calculated can be used as a representation of how many atoms we have in the compound. Okay, so hydrogen is 13.13 and its molar mass is 1, and we're going to be given 13 atoms, and the oxygen is 34.75 divided by 16, and that gives us 2 atoms. So when we put this together in our chemical formula, which is our final step, that is C4H13O2. Okay, okay, let's move to our next question. So our next question says, determine the empirical formula for nicotine when the compound has 74.03% carbon, 8.7% hydrogen, and 17.27% nitrogen mass percentage. So nicotine is, I'm sure most of you know, nicotine is found in cigarettes. So we're going to calculate how much carbon, hydrogen, and nitrogen, how many atoms of, how many individual atoms are present in the compound. Okay, so what was our step one? What was our step one? Our step one was to assume 100 grams of sample. So that means carbon has 73, that should be 74.03 grams. Yeah, please make sure you change that there. It's supposed to have been 74.03. Okay, and I have a calculator here, so I guess I will work through it. The mass percentage of hydrogen is 8.7 grams. The mass of nitrogen is 17.27 grams. Okay, so the next step was to calculate the number of moles or the number of atoms, right? So our mass of carbon was 74.03 divided by the molar mass, which should give us 6.16, not 6.08, and that would still be rounded off to 6 atoms. Okay, the number of moles or number of atoms present in nicotine, that is 8.7 grams divided by 1, which is 8.7, and we'll round that up to 9. And nitrogen is 17.27 divided by 14, which should give us 1. Okay, so the empirical formula for nicotine is C6H9N. Okay, so if there's any questions there, please let me know and I will help you as best I can. Okay, but it's a very simple process to understand, and um, it's a very easy section to score marks. Okay, so percentage yield, I think, is the most important of the three, because Sometimes when you're doing chemical reactions in the lab, you calculate how much mass you're supposed to get, but it turns out that you get less or you get more. So it's important to know that percentage, whether it's below 100% or whether it's above 100%, or ideally whether it should be 100%. Okay, so percentage yield is a method uh, that can be defined as the amount of product formed once a reaction has been completed in percentage form. Now, percentage yield can be calculated using the formula percentage yield equals to actual yield. Now, that's the yield you get, or that's the amount of product you get after your experiment is done. Is the amount of product you calculated and the amount of product that you should get or you should expect to get, and times 100, which will give us our percentage. So the amount of yield produced depends on a number of factors. The limiting reagent. The limiting reagent depends. If the limiting reagent gets finished, then obviously you won't have 100% of yield because you'd still have an excess reagent and a reagent that still needs to be used up. Lab discrepancies, maybe you put in too much of acid, or maybe you dried your compound too much to decrease the amount of mass, or your um, final product has too much of water in it, which means it's going to get a percentage yield above 100. So that falls under lab discrepancies. And as I said, the excess reagent depends on uh, the amount of yield depends on the excess reagent. So we're going to look at an example. Example says a student reacts 15 grams of magnesium hydroxide with 10 grams of sodium chloride to produce magnesium chloride. The student noted formed 10 grams of product. What is the percentage yield of the product formed? Now, as we can see, we have magnesium hydroxide and sodium chloride, and we have magnesium chloride. And the first thing you'd notice is that one, we need to know the chemical formulae for these reagents and products. And the second thing is we need to know how to write up a balanced chemical equation. So let's look at that. The first thing we do is we'd write a balanced chemical equation, and that would be magnesium hydroxide plus 2NaCl goes to MgCl2 plus 2NaOH. Let's look at that quickly and see if it's balanced. We have one magnesium on the reagent side and one magnesium on the product side. We have two hydroxides on the reagent side, and we have two hydroxides on the product side. The 2 is distributed to the O and the H, which gives us two hydroxides, and we have two sodium atoms on the reagent side and two on the product side, and finally we have two chlorine on the reagent side and we have two chlorine on the product side, which means our reaction is balanced, and now we can proceed. So step 2 would be determining the limiting reagent, which is what we did yesterday. We tried to calculate the limiting reagents of reactions. So what was the first step for to calculating the limiting reagents? The first step was to calculate the number of moles of each of the reagents. Now you're going to have your periodic table here again to calculate the molar masses of each of the compounds. Okay, so we have 15 grams of magnesium chloride and your molar mass for magnesium chloride would be 58 grams per mole, and that would give us 0.26 mole. And we look at NaCl, which is 10 grams of NaCl over also 58 grams per mole, and that would give us 0.17 mole. Okay, now what was our second step? We have our moles. Now we look at the stoichiometric ratio and we divide our reagent number of moles by the stoichiometric ratio. So what that means is magnesium is 1. Magnesium has a 1 here. So we take 0.26 and divide by 1, which would give us 0.26. And we have a 2 by NaCl, and we divide NaCl by the 0.17 and we divide it by 2, which should give us 0.085. And now we judge. Now, what the stoichiometric ratio tells us is that 1 mole of magnesium hydroxide has to react with 2 mole of NaCl to form 1 mole of MgCl2 and 2 moles of sodium hydroxide. So once we divide it, we can see that the number of moles of sodium chloride would be less than the number of moles of magnesium hydroxide, which means that the NaCl is going to get finished a lot faster than the magnesium hydroxide, which means that NaCl is our limiting reagent. And you can see now from the ratio, it says down at the bottom, from the ratio 1 mole of magnesium hydroxide reacts with 2 moles of NaCl, and that would mean 0.26 mole of magnesium hydroxide would react with 0.086 mole of NaCl, which means NaCl will get completed much faster. And if we do a quick calculation, we'd see that 0.17 mole of magnesium hydroxide is in excess. Okay, so step 3 of percentage yield, we now determine the mass of the product. Now we have to use the mole of our limiting reagent. Okay, so we look at NaCl and we say, okay, 1 mole sodium hydroxide, 1 mole of magnesium hydroxide reacts with 2 mole of NaCl, and the product we're looking for is magnesium chloride. So those two reagents react to give us 1 mole of magnesium chloride. So we're using our NaCl because it will get finished faster, and it is our benchmark and our threshold for how much of product would be formed. So to determine the mass, we're going to have to say from our stoichiometric ratio, the number of moles of NaCl equals to half the number of moles of magnesium chloride, because you have 2 moles reacting with 2 moles sodium chloride reacting with the 1 mole of magnesium hydroxide to give us a 1 mole of magnesium chloride. So which means that NaCl is 2 times larger than magnesium chloride. Okay, that's why we're dividing by, or we're multiplying by the half. So that will give us 0.086 mole of magnesium chloride. Now we have the number of moles and we have the molar mass of the compound, which we calculated by now. and that would give us 0.086 mole, which equals to the mass that we're trying to calculate, and that's divided by 95, which is the molar mass of magnesium chloride, and the mass is 0.086 multiplied by 95. We just made the mass the subject of the formula, and we get 8.17 grams. So let's go back quickly, and we have 10 grams of product that was formed, okay, and 8.17 grams is what we have. Okay, so as you can see that 10 grams is what she actually got, and we only calculated 8.17 grams, which means there was some lab discrepancies that happened. Okay, so percentage yield equals to actual yield over theoretical yield. Oh, we need to change this. So we get actual yield is 10 grams, and that's divided by 8.17 grams, because that is our theoretical yield, and we should not be getting an answer below 100. So that's 10 divided by 8.17. Why is it 10 as the actual? Because what she told us here is that there is 10 grams of product that is formed, and now we had to change those values. Okay, so if there's any problems, please contact me and I will help you out. So that's 10 divided by 8.17 times 100, which equals to 122.4%, right? So that was supposed to have been the percentage yield. So let's go through that quickly one more time. We had to change our values. I made a mistake. I'm sorry about that. And our actual yield was 10 grams, but the yield that we were supposed to have gotten was 8.17. So you can see that maybe there's too much of water in her product, or in the student's product. And 10 divided by 8.17 grams times 100 would give us a percentage yield of 122.4%, which means that from the reactants, that is how much of MgCl2 we have, which is 122.4, when in fact we're supposed to have 100%. If you get an answer in a test or exam that is above 100%, please do not panic. Maybe it was supposed to have been that way, and maybe you would have to answer some supplementary questions on why you have a yield greater than 100%. Okay, so that is the end of today's lesson. I will be sending out homework for everyone to do. They'll have questions on percentage yield, questions on empirical formulae, and questions on mass percentage. So please work through that, and if you have any problems, I will help you through those problems. Okay, thank you. Have a good day. Bye.